Okay, let's talk about benzene, aromatic compound. I'll cut to the important thing right up front so you have the So there's three key points for something to be what we say is Kuckel aromatic. It's named after the guy that proposed it. There have to be 4n plus 2 pi electrons, where n is an integer. So 2, 6, 10, 14, etc. Right? So it will be Kuckel aromatic. It has to be a cyclic structure with a continuous ring of sp2 hybridized carbons. So you can't have any sp3 hybridized carbons in the ring. If you do, then it's non-aromatic. So benzene fits the bill. It's a 6-membered ring, which means there are 6 pi electrons. And all of these carbons are sp2. But cyclohexadiene does not fit, right? Because cyclohexadiene has sp3 hybridized carbons. So that's not a continuous ring of sp2 hybridized carbons. Cyclopentadiene also doesn't fit. There's an sp3 hybridized carbon here. But cyclopentadienyl anion or cation could fit. Took one of those hydrogens off to generate the anion. Now we have 6 pi electrons, and this is now sp2 hybridized. So cyclopentadienyl anion is actually aromatic. It's not the number of carbons or the number of atoms in the ring that matters. It's the number of electrons in the cyclic system that determines whether it's aromatic. So try not to confuse the number of pi electrons with the number of atoms in the ring. It's often the same, especially if those atoms are mostly carbons, but it doesn't have to be the same. So another molecule that is Kuckel aromatic is pyrrole. Pyrrole actually has 6 pi electrons. Normally, a trivalent nitrogen like that would not be planar. Right? Normally, ammonia would be pyramidal. And sp3 hybridized. But by going to an sp2 hybrid orbital, going planar, we can generate a 6 pi orbital of 6 pi electron system, right? 5 pi orbitals with 6 pi electrons. We can make it aromatic. So it has an incentive to go sp2 hybrid to create that aromatic stabilizing energy. As a result, this is not basic, right? Most nitrogens are basic. This can pick up a hydrogen to make NH4 plus, and the pKa of NH4 plus is around 9. Pretty weak acid. Yeah.
Why is it a 5 pi orbital again?
Because there are 5 atoms in the ring. 5 pi orbitals, so each atom brings a 2pz orbital to make orbitals from. Benzene will be a 6 pi orbital system as well as 6 pi electrons because there's 6 atoms. So the number of pi orbitals is controlled by the number of atoms in the ring, but the number of pi electrons can be the same as it is for benzene, but it can be independent because you might have a lone pair, or you might have a cation. It might be nothing on there, in which case you have a 4 pi orbital system, or 4 pi electron system. But a 4 pi electron system is not aromatic, because it's not 4n plus 2, it's 4n. So things with 4n pi electrons are actually called anti-aromatic. And those are less stable than they would be if they were not a continuous ring of hybridized carbons. So in some cases, they don't even go aromatic. So this pKa is 9, right? That's a pretty weak acid. If pyrrole picks up a hydrogen, it actually picks it up not on nitrogen, but on the carbon. And the pKa here is minus 4.4. Which basically means that this lone pair is not basic. Huge difference between minus 4.4 and 9, and the nitrogen doesn't even get protated. It's one of the carbons in the ring that gets protated. The reason for that is if you protate one of the carbons within the ring, you can actually write 2 additional resonance structures for this. Stabilize it a little bit. Whereas if you were to protonate it on the nitrogens and generate an sp3 hybridized nitrogen, there would be no ability to draw resonance structures because you can't actually get rid of the positive charge on nitrogen by expanding the octet. Right? So because that lone pair in pyrrole is part of an aromatic system, it's not free to react as a base. Right? It's interacting with these pi bonds, and when the proton comes and says, dude, I'd like your lone pair, these 2 pi bonds say, nope, we've already got that lone pair, you can't have it, screw off. We're going to, stay aromatic. So the question we want to address is, why is 4n plus 2 pi electrons special? What is it that causes that aromatic stabilization energy? And it's a really big stabilization energy. The aromatic stabilization energy is almost 30 kilocalories per mole. So, in contrast, the stabilization energy for our conjugated diene rather than 2 isolated alkenes is about 2.3 kilocalories per mole. So the aromatic stabilization energy is dramatically larger. So we need to look at the orbitals to determine what it is about the molecular orbitals that causes that to be much more stable. So what we want to do is we want to compare the orbitals for benzene to the orbitals of just a plain linear 1, 3, 5 hexatriene to see if we can understand why they're so much lower in energy. So if we look at 1, 3, 5 hexatriene, this. Okay, we're starting at the bottom. So it would look like that. 3 field orbitals on the bottom, frontier would be between the HOMO pi 3 and the LUMO pi 4 star. And remember that this has 5 bonding interactions. This one has 3 net bonding. This one has 1 net bonding. This one has 1 net anti-bonding. 3 net anti-bonding. And finally this one up here has 5 anti-bonding. So there's a difference in 2 net bonding interactions. Right? We decrease the number of net bonding by 2, then we decrease it by 2 again, then we decrease it by 2 because we get rid of the net bonding and we introduce a net antibonding, and then we increase the net antibonding by 2 and we increase the net antibonding by 2. So that's what that looks like. And we can draw those orbitals. We can show that there are no nodes for pi 1. Pi 2 has that single node down the middle. Pi 3 has 2 nodes. And you notice the symmetry changes each time. And so we change from a sigma symmetric to a C2 symmetric back to a sigma symmetric. Pi 4 has 3 nodes. This is the way you drew on the quiz. Let's take it back. Over here, you shouldn't have to write this down. Pi 5 is have 4 nodes. This. And Pi 6 has nodes everywhere. This is our comparison. That's our comparison molecule. So if we look at energies, the way we measure these energies is by hydrogenating phase. And all 3 of these molecules when hydrogenated, generate the same material. They all generate cyclohexane. They have to be given a little more hydrogen, right? 1 mole, 2 mole, or 3 moles of hydrogen. So it turns out that when we hydrogenate cyclohexene, it releases 28.6 moles. So we would predict that if we would hydrogenate 2 double bonds, right, we might get 2 times 20 minus 28.6. So that would be minus 57.2. Dying, but we actually observe not minus 57.2, but minus 54.9. So the difference between these two which is 2.3 kilocalories per mole, that's due to conjugation. That would allow us then to predict what we should see. I have calculated value for this. Of 3 times minus 28.6 plus 3 times minus 2.3 Because we've got conjugations in 3 different locations. And we've got 3 pi bonds. So we might predict 3 times minus 28.6 plus 3 times minus 2.3, which is 3 times 30.9. And we would say that we should see minus 85.8. No, sorry, wait. Is that right? So minus 78.9. You should see minus 78.9.
What you're doing with the plus sign, plus and then negative.
Plus sign
Never
here.
mind.
There we go. So we should release 28.6 kilocalories per mole for each pi bond that we're hydrogenating, but then we should get back 2.3 kilocalories per mole of conjugation stabilization energy.
It's minus 78.9.
Yeah, so minus 78.9. That's what we should release if it were just a cyclic pi system and no aromatic stabilization. So it would go from minus 28.6 kilocalories per mole to minus 54.9 kilocalories per mole to minus 78.6, right? Because we've actually got 2.3 kilocalories per mole less energy being released here than we would predict because of the stabilization energy. It's already 2.3 kilocalories per mole more stable than it should be if there were no conjugation. So what we would predict is this would start at 3 times minus 28.6, but then it would be 2.3 kilocalories per mole more stable for each of these 3 interactions. So it wouldn't start out as high. So what do we actually see when we hydrogenate benzene? We add 3H2, hydrogenate that, and convert it to cyclohexene. Delta H of hydrogenation. Minus 49.3. We've already predicted that it should be 6.9 kilocalories per mole most stable as a result of the conjugation. But in addition to that, it's now, this is minus 49.3. So it's now another 29.6 kilocalories per mole, even more stable. You take the minus 78.9 kilocalories per mole. I don't actually bother remembering these numbers, and I just use if I have a book open. So we get 29.6 kilocalories per mole aromatic stabilization energy. That's the only number that's worth remembering, and you might as well round it to 30. So basically, by putting these 3 double bonds in a continuous ring of sp2 hybridized carbons, we have generated a molecule that is now 30 kilocalories per mole more stable than it should be, based on just having 3 double bonds and having conjugation. That's a lot. That's way more than the 2.3 kilocalories per mole stabilization energy that we get from just having a conjugated diamine within the ring. So where did that come from, right? What is it about the orbitals? The orbitals must be more stable. These guys, these bonding orbitals, where the electrons lie, have to be lower in energy for the benzene ring than they are for 1,3,5-hexatriene, to explain why tying them up in a ring like that causes them to be so much more stable. This whole thing is on page 671 in your text. So if you ever want to look those numbers up again and see the same kind of calculation. But here's the key, right? It's about 30 kilocalories per mole aromatic stabilization energy that we need to explain from the orbitals. So what's the difference between a cyclic pi system and an acyclic pi system? That's what we have to address. And the difference is we now have a molecule that lies in a plane rather than lying along a line. And if the molecule lies in a plane, we have degenerate orbitals. There are two different ways of cutting a sheet of paper in half. There's only one way to cut a string in half. So when you have a plain sheet of paper, you can cut it on the vertical. You can also cut it on the horizontal. So there are two different single node orbitals. As opposed to a string, right? Only one way. So there was only one way to have a single node orbital here, pi 2. Pi 3, we had to end up with 2 nodes. But now both pi 2 and pi 3 for the cyclic pi system are going to be single node orbitals. So what we need to do is we need to look at benzene. And we need to draw all the possible ways that we can create molecular orbitals from it. So we've got our cyclic system. Throw our bonds in there, although that's not really necessary. We've got the orbitals. And then we need to put our orbitals on there and figure out where they come from. So it's probably pretty obvious that the most stable thing you can possibly do is have all of these orbitals in phase. And so we have the positive lobe of each orbital pointing up. We have the negative lobe of each orbital pointing down. That's going to be pi 1. And that's going to be the classic benzene orbital that you can see. It's got a donut on the top and a donut on the bottom, where the electrons interact simultaneously with all 6.
If we were to flip it and do negative on the top, positive on the bottom, that's the same thing, right?
Wouldn't matter. The reason it doesn't matter is the radial probability function, which is what tells you where you might find the electrons, goes as the square of the wave function. Right, so everything's positive on the radial probability function because when you square it, you get negative numbers. What's important is that they're in phase. How many net bonding interactions are there?
5. So it's 6 because it's in a ring.
There's an extra net bonding interaction that we didn't have in the acyclic system because now these two ends are tied together. And since they're in phase, because it's a sigma symmetric orbital, you get an extra bonding interaction. So there are 6 net bonding interactions here. That is the origin of the aromatic stabilization. Pi 1 is lower in energy for benzene than it is for cyclohexatriene because of that additional bonding interaction. Probably fairly obvious that pi 6 star, right? That's going to be the one that has nodes everywhere. Everybody's out of phase. It's always easy to do the ends. Right? So there are 3 nodes. You'll notice that 3 nodes is fewer nodes than the 5 we had, right, for pi 6 star for the acyclic system. But it's worse, because with just 3 nodes, how many antibody interactions do we have? 6 antibody interactions. It has to be 6, right? Because if this drops by a certain amount, this has to rise by the same amount. And what that means is pi 6 star is going to be higher in energy than pi 6 star for the 135 trigon. So let's put the orbital energy diagrams on the same energy scale. Energy looking like this. We have our cyclic system here, and our acyclic system here. Original E. Got these kind of evenly spaced. Right. Hopefully those are roughly evenly spaced. And now for this system, we drop pi 1 and we raise pi 6. The fact that we raise pi 6 isn't really important because it's empty. But the fact that we drop pi 1 does matter. What we really want to do is we want to create a bunch of low energy orbitals and fill them, and a bunch of high energy orbitals and leave them empty. So now we need to look at pi 2 and pi 3, which will be bonding. And we need to look at pi 4 star and pi 5 star, which will be anti-bonding, right? And figure out how many nodes they have, where those nodes are, and all that stuff. But we're overdue for a break. So let's take a break, and then we'll come back and we'll look at the rest of those orbitals.